Okay, let's start today's class. So today we are gonna talk about transforms, which are Fourier transforms and Laplace transforms. So we start with Fourier. What is a Fourier transform? So this is a theory that every function can be approximated by a combination of sine and cosine functions. So Fourier transform basically is a way to decompose a function, any function you give it, and from the space of time into the function depending on the frequency, which we'll call it in frequency domain. So like this, on the left side, there's a function. It could be either maybe an electric signal or like a vibration of something. So you get this data, and you can by using Fourier transform, you can decompose it to like the right side into multiple sine function, and then you get the plot on the right, which is, we call it frequency domain, because the x-axis is a frequency. For the frequency 1, we have the magnitude of 4. For the frequency 2, we have the magnitude of 0.5, and so on. And all this represents this signal. So it's like this. Any function like this, it can be approximated by multiple sine or cosine. They are actually the same, just a different phase angle to approximate a function. So this is how you calculate the definition of Fourier transform. The upper one is a definition, and the lower one is if you use discrete sample points. So what is sample point? On the top one is you input the whole function into it and calculate. So you get a whole function. But with this, you only give it data, like what we did with plotting. We give it a series of data, series of x and y, and it will calculate those as those are, we call it sample points, and we calculate it by this formula. But we actually don't need to write all those by ourselves. The MATLAB already did it for us. So for continuous function, the top one, this is a sample example MATLAB code. So here we got it. So to define a function, of course we have to start with SYMS, symbolic. And here we use it as t. And then we define our function. a rectangular pulse of magnitude 1 and between 1 and 2. So it gives us this on the time, when the time reaches 1 second, it gives you a magnitude of 1 until the 2 second, and then it disappears. So this is our function, continuous function here. And then we use this code Fourier to let it calculate the Fourier transform for us. And this is the Fourier transformed. As you can see, it's in W, or it is actually omega, which is the frequency. So it becomes a function of omega, a function of frequency, not a function of t anymore. And so we get this plot, which means it has like -1. Actually, we shouldn't look at the negative. For the frequency 1 Hertz, we get like approximate 0.95 of the magnitude. So if you can go with all these numbers and do it and type it into a sine function, you will actually get this function back, get this rectangular impulse back. And something to say, this, how do I do this? 2 plots in 1. It's called subplot. Subplot right here. So what does a subplot do? Subplot, you define where, how many plots you are gonna have. So 2 means 2, 2 in a row, and one column only. 是这样，还是我讲相反的 ？row 跟 column。So this means 2 in a row and and only 1 column. And 1 means now you are plotting the first picture, and then now you use the regular plot. You can either use plot of f plot or anything, any graph you learned before, and then it will be assigned to the first position. So this is the time amplitude plot right here. And then you assign him to the second plot. And then you plot it again. So this one, it will be assigned here on the second position. Oh yeah, rectangular pulse. So this is a rectangular pulse. It's a function just like this. So it means this is the variable, and this means where it starts, and this is where it ends. So on 1 second it starts, and on the second it stops. So back to 0. Yeah. Hmm? You mean this? Oh, F plot.
No, not F plot. Abs.
Oh,
Abs.
F's is absolute, because use Fourier transform, as you can see, it's actually a complex number. So to plot is to give a proper graph, you need to give it absolute. Yeah. So let it plot its magnitude. So it won't, if you don't do this, it will plot, I think it will give you an error, or maybe a plot with a complex, in a complex domain. Yeah. So this is a way to do a continuous function. And then a second way to do the Fourier transform is to use a discrete sample points. So there are actually more lines right here. So for the first line we have here is the sample time. Ts is the sample time. So you want it to have a sample point every, this is 0.02 second. Every 0.02 second, you want a sample point. And this is the total period of time you want to see, 0 to 10. And then here is your function, x, which is composed of two sine. One is of 20 Hertz, and the other one is 15 Hertz. And then the rest, and then you plot the function first. And then this is the Fourier transform, FFT. This is, you use Fourier if you are defining a function. And you use a FFT if you use the sample point. Yeah, so that's how this plot comes out. So as you can see, this is composed of a signal of 15 Hertz and a signal of 20 Hertz. So in frequency domain, you get a number in 15 and another in 20. You get two spikes here. And this is the 30 and 35, this is just a mirror image. So you can just don't look at this. And the magnitude is 1, and this is the 20 Hertz one is twice of the 15 Hertz. So you can see the magnitude, this is twice of this. The spike is twice as high as this. So this is how Fourier transform works. And then you have inverse Fourier transform. Which means you actually go back to what you have defined for, like this. So this one is what we had with the rectangular impulse. And so if I put I Fourier of f, so we have a small f and a big and a capital F is a Fourier transformed version. And then now we convert it back, and let's say it is f2. And then we can plot it. And because there's 3 plots, so I'm gonna do this. And we'll let it run. Oh, I forgot to clear the workspace first, because now it's on the so as you can see, the third figure is we had it Fourier transformed and then transform it back. It's the same as the first plot, exactly the same. And for the sample points, for the way using sample points, it's basically the same. Just use IFFT. It means inverse FFT. So you will get the original function back. And these are just some more things that you can take a look at if you want to dig deeper inside this. And we go to Laplace transform. So it actually converts a real variable to a complex variable, which is S domain. And I'll just so Laplace transform is actually very good for solving ODEs, ordinary differential equations. I think you should have learned this in engineering mathematics. Yeah. So in an initial value question, when you use Laplace, you get the equation like this. So in MATLAB, it can calculate all these for you. This one. like this. So this is a differential equation. Actually, two differential equations. And using a Laplace, it's just called a Laplace, and then you will get the transformed. And it actually teaches you how to, step by step, how to use it. So I'm not gonna cover all this because we are not an engineering math class, we are a MATLAB class. So I'm just here to tell you that there's Laplace transform in MATLAB, and you can use it. So I won't teach you, I'm not here to teach you how to solve the ODE. So the simple version is right here. Let me clear the command window first. So you define a function using symbolic SYMS. And right here we define it in x. And this is x square root, 1 over square root x. And we Laplace transform it. As you can see, now it's in S domain. There are lots more examples like exponential, and you get all this. So you don't have to, with this tool, when you do homework, you don't need to actually go find the transform chart and calculate it by yourself anymore. You can just type it in your function and just Laplace f or any function you defined, and it will give you the correct answer. Yeah. I guess that's it. And the homework. Just find any function you like. You define your own function and do Fourier transform and plot a figure like what I just did, two figures, a time domain figure and a frequency domain figure, and then do a Laplace transform. You don't need to draw any plots with Laplace transform. Just give me just an answer like this. And I see some of you actually put your name in the file title. Don't do it, because MATLAB, it can only run files that are English. If you put Chinese on your file name, it can't actually run. So we have to modify your file before we check if you are correct or not. So don't put your name. Just student ID and TA homework 6.m. Okay, any question? Any more questions?